couple quick announcements. The proposal for the project is due today. I noticed the form that Eric set up requires 2 entries. There's been a very small number of people that have asked for special consideration to do the project independently. You have to, by the way, but if you want to do that, you have to ask me to do that beforehand, and you have to have a good reason why you want to do that. But if you do have all those things, then I may approve it. So we'll change the form to allow that for those small number that have already gotten that permission. Homework 4 is due on Wednesdays, everyone I'm sure knows. The other thing is that mid-semester grades are out today. But don't take them too seriously. Just because they're only going to cover so far 3 homeworks, you sort of know how you did on the homework. And the translation to letter grades is really kind of inaccurate because unlike, say, the tutorial and the project, partial credit's a little harder for the homework. So there might be a bigger gap than you might think. So if you're on the low side, really don't worry about it. If you are concerned about your grade, please come see me rather than just think it's going to be a bad grade. Chances are it's actually nothing to worry about, but just let me know if you do have any concerns. Those are going to be out today, though. And then finally, here's the results of the survey that everyone took for homework times. I'm sure you're all very curious where you stand in regards to this. So I'm showing here the medians time spent per homework for 688 and 388 for the SCS students and other schools. And it's about in line where we were shooting for the most part. This is about right. It's supposed to be 6 hours per week, so that's about 5 hours per week, minus the other weeks that people don't spend, minus the other weeks that you don't have homeworks due. This is a little bit on the high side, but then also sometimes people don't quite have the background. And so you have to just, not that you don't have the background, but that you have to, make up a little bit more time with some of the homeworks. These are a little bit on the high side. I'm a little surprised that, the one extra question takes that much more time. And I suspect this is actually probably caused largely by what I talked about on Friday, which is the lack of description about the API calls you need to use on the homeworks. And I think this is probably what's causing the majority of time spent on the homework. So I'm very hopeful that the recitation that we had on Friday, everyone heard about that, right? We have a recitation on Friday. And we're going to have this for the next 2 homeworks. The next 2 homeworks, it'll be the Friday after the homework's released, so you'll have more time to use that. And hopefully this will kind of address some of the longer terms, especially some of the heavy tails. The median's 30 hours here, but there's a very, very heavy tail with some people upwards of 70 or so they claim per week, per homework. Which may be if you don't. If you haven't seen all this before, actually maybe it seems a lot, but it's certainly possible. There's a question there.
Yeah, so I don't know if you want some comments as a 688 student. The fact that it's like the one extra, so it's not just like one question, but an extra notebook. And usually from what I've seen, like since 388, there's a lot more students on 388. The 2 notebooks that are part of 388 has a lot more questions and explanations on Piazza while 688 notebooks, while having less questions.
Yeah.
With them also have a much less strict guidance.
I see.
Like for the XML parser, for example, it was very open-ended.
Yeah.
The other ones kind of like hold you from your hand, like walk you through step by step.
Okay, yeah. So we can talk about that offline maybe a little bit. There's actually many more students enrolled in 688 than 388. So yeah, quite a few more. So I'm not sure it's just due to the volume of the class, but I suspect that the open-endedness of the question might make the fact that you don't know which APIs to use that much more time-consuming because you have to search through that many more things. So we'll see if this addresses it. I'm hoping that it will. There isn't, unfortunately, much time to correct after this, but this is sort of the problem with shortening the homeworks too much is that we lose a lot of the actual content we're covering, of course, right? We can't, a lot more content is to come, and we want to cover some of it. So that's kind of where we stand. We'll feel things out and try to adjust based upon how people respond and how people are sort of feeling with the tutorial and the project. But this is our current plan. Stick with things as they are, have these recitations though, and try to adjust the homeworks to sort of fit these results. Maybe making the 688 one question a little bit on the shorter side than it currently is. So that's sort of where we currently stand. If anyone has any thoughts on that, by all means, send us an email. Okay, so let's jump into finishing up a little bit from last time. Today's going to be largely talking about hypothesis testing, but I want to finish up with a few additional comments from the last lecture on probability. And so the last thing I want to mention when it comes to probability is talking about machine learning in the context of maximum likelihood estimation. So I went through machine learning, and I didn't really talk about probability at all, right? I hadn't covered probability yet when I talked about machine learning, which is somewhat odd in some views because machine learning is very closely intertwined with probability. And I talked about it just in terms of really hypotheses and loss functions, right? So you're just trying to minimize a loss function. And so all I want to point out here is that most machine learning algorithms actually have a very concrete probabilistic interpretation as well as the one that we covered in class. Not all of them. Some are just not probabilistic at all, really. But a lot have probabilistic interpretations. So think about logistic regression as an example. So this algorithm minimizes the sum of logistic losses between the hypothesis and the true output, where the logistic loss is defined as the log of 1 plus the exponential of negative y times the hypothesis class. And you remember that kind of looks like a curve that kind of slopes upward linearly and then tails down to 0 in the positive direction. So if you're very confident wrong, you get kind of a linear loss penalty for that. And if you're very confident right, you start going towards 0 loss. But the important point here is that logistic regression actually has a very nice probabilistic interpretation. And in fact, this is often how it's posed the first time. I didn't pose it this way because I wanted to kind of highlight the connections between the different algorithms more closely. But this is sort of the common model for talking about logistic regression. And the idea here is that we're going to posit a probabilistic model of the output y given the input and parameterized by our parameters theta, which are our machine learning parameters. In particular, logistic function, this is supposed to be 1 over 1 plus the exponential of negative y, well, y first. Negative y h theta of x. Where for a linear function, then, this is just often e.g. equal to theta transpose x, right? And this is a function called the logistic function. And it looks, or the sigmoid function is also sometimes called, and it looks kind of like a little s function, where as you go to infinity, the function approaches 1. As you go to negative infinity, the function approaches 0. And at 0, it's 0.5. And so this is a function that kind of very naturally captures probabilities, because remember, we're talking about binary valued output variables. Oh, sorry, I should have actually written, yeah, okay, this is y here is not 0 or 1. It's actually negative 1, 1, but it's mapping to a probability. And so the probability of y being negative 1 or positive 1 is you just substitute negative 1 or positive 1 into that expression. And the nice thing about this model, and I'm not going to go into this in too much detail because it's actually, I don't have time to kind of justify why this model is a good one. There are some reasons why this model is actually a very nice one mathematically. But you can kind of see just sort of intuitively, what it's doing very nicely is it's taking this hypothesis function, and it's mapping that. And actually, this is, for example, the hypothesis function. So this would be the probability of the class being positive. It's mapping that very nicely to a probability. So remember, what we sort of said was that we have this x-axis here, which is y times our hypothesis function. Over here, this is the 0 point. Over here means you're very confident, correct. And over here means you're very confident, but you're incorrect. And that translates to a probability, being the over here, I think the probability of the class being that is 1. And on this way, I would think it would be well, the class would be 0, but then I would be getting it wrong, actually. And so what this is saying here, and this is sort of as far as I'm going to get with this, is that if we take the maximum likelihood approach to estimating parameters, which remember is you find the parameters that maximize the sum of log probabilities of the data. If you take that approach, in other words, this maximum likelihood approach, plugging in that probability for the probability here, you'll get exactly the logistic loss function. So essentially, that function, the log of it, is the logistic loss function. So that's as far as I'm actually going to say. All I mean by that is just to really know that there is this probabilistic interpretation, which you can actually also use too, right? So if I want to know the probability that my output is equal to 1 from my with my trained logistic regression model, I can substitute the hypothesis function into that expression there and get a probability is equal to 1 and a probability is equal to -1 also, which is just 1 minus, of course, the probability is equal to 1. Okay, so the only point I want to make here is that these loss function based models often have other interpretations, and we didn't just sort of pull these things out of thin air. There actually often are sort of very nice rationale for why we use these loss functions. The same thing happens for least squares. So if I assume that my data is, so remember, least squares talks about minimizing some loss between my prediction theta transpose y and my actual y. But if we assume that the actual y is generated by a probabilistic model, y actually equals my hypothesis. I'll just use a linear function there instead of the hypothesis more generally. Plus some noise, where here epsilon has a normal distribution with mean 0. It's important that it's mean 0 because you don't want to have, if you have a non-zero mean noise, then you're actually having a bias to your estimator. 0 mean noise and some covariance sigma squared. In other words, it's the same thing as saying that the probability of y given x, parameterized by theta in this case, it would actually be parameterized by theta and sigma squared would be, if you want to be technical about it, you'd have both those as parameters. That is equal to a normal distribution with mean theta transpose x and variance sigma squared. At least you know why they put that thing in there. Probably took a lot of effort to get it in there, but it didn't do this before. Okay, so if we have this model now, right? So if I posit this model, in other words, my true, I believe, or I'm going to assume rather, that my outputs that I'm observing are genuinely some function, some linear function of the inputs, plus some Gaussian noise. Then, and if I maximize the log probability, the log likelihood of the parameters of my model under that assumption, what I get is I get a minimization of the squared error. And that's hopefully not too hard to see. Remember, this thing here is equal to 1 over square root of 2 pi sigma squared times the exponential of negative. This is a scalar, so it's just going to be 1 over 2 sigma squared times x transpose y minus y squared. Right? That would be the log. That would be the probability of y given x. If I take the log of that, all that's left is this times this term. Right? This is a constant that doesn't have where theta doesn't factor in here. The only things that depend on theta here is this term. It's scaled by 2 sigma, but actually that just adds a scaling factor to this thing, so we can ignore it for finding theta at least. And maximizing the log probability there is actually equivalent to minimizing the sum of squared errors. So again, sort of very, very sort of high level here. I just want to emphasize that these things have interpretations that are beyond just the squared loss as a nice distance metric. And so you might want to actually think about, if I know my distribution of my data, I might want to use that to inform the loss function I'm going to use for my machine learning algorithm. You can do other things too, by the way, like if you use an absolute loss function, that's equivalent to doing maximum likelihood with a Laplace distribution as your distribution of the errors. So this is Laplace distribution instead of a normal distribution, which we covered briefly. It essentially looks like a normal, but just has absolute values, and so everything sort of works out the same when you take the log bit. Okay, the last thing I'll say here, and again, this is not meant to be, these things are going to need to derive for this course at least, but they're good to know about. The last thing I'll say here is an interesting connection between logistic regression and naive Bayes. And so we're not going to discuss this too much, but it actually turns out if you write down the functional form of the predictions that naive Bayes makes for certain inputs and assuming certain models, either a Gaussian model or a Bernoulli model, or some others as well. In both those cases, it turns out that you can write a linear model that can give the exact same predictions. So what I mean by that is, when I go through my whole naive Bayes sort of work, and actually I'm coming up with the probability of y given x. Yeah, there it goes. All right. Given all my parameters. Remember, for naive Bayes, these parameters essentially are things like Bernoulli models of each individual feature given all the other given the class label and independent of all the other features. But if I actually sort of write this in a certain form, you can actually show that this is also equal to some other set of parameters times a feature vector, which I'll write as phi of x. That essentially just enumerates the values that x takes. And so actually, it turns out that naive Bayes has a very similar linear model in some sense to what logistic regression actually also typically has. The difference, though, so in machine learning talk, what that means is that the hypothesis function, the sort of the state of all possible predictions you can make, or the set of all possible predictions you can make for logistic regression and naive Bayes is actually can be very similar. It turns out those things are actually very similar, and you can sort of there's under the right assumptions that there's a very nice equivalence between those two. If people are interested, I could, by the way, point to more sources here. This is very hand wavy, I'm aware at this time. But the difference is, there's an important difference, and that is logistic regression minimizes this conditional likelihood. So we're setting up directly a conditional model of y given x, and we're minimizing the likelihood of that conditional distribution. Whereas where we don't care in logistic regression about the distribution of the x's themselves, right? We're not trying to model any distribution over the x's. We're just trying to model the distribution of the y given the x's, right? Well, it turns out that naive Bayes is actually trying to maximize the joint distribution. And by the way that you sort of see that is, remember that in all our probability models for naive Bayes, remember the way we estimated the parameters was we just used maximum likelihood estimation over each parameter individually given the class label. That corresponds to actually also a maximum likelihood estimate of those parameters, which corresponds to maximizing the joint likelihood of x's and the y's. So what we're doing in some sense with naive Bayes is we're actually maximizing the joint likelihood of x and y. So unlike some other algorithms, it actually turns out that what's different between naive Bayes and logistic regression is not the hypothesis class, but actually the loss function you use. So other than that, they're actually very similar. Again, I'm being hand wavy there, but they are very similar. But it turns out that they are minimizing or maximizing, or minimizing very different loss functions in their representation. So those 2 points, the maximum likelihood interpretation and the differences between naive Bayes and logistic regression, those are not meant to be very detailed here. They're meant to be kind of a high-level overview. There's a lot more sort of resources you can go into if you want more information about that. But I did want to highlight those connections because I think they're important to sort of get a understanding, at least, that machine learning itself has a lot of these interpretations that it can go with. Yeah?
So would logistic regression be like a better estimator or classifier since you're not doing the independence assumption?
So it's actually interesting. So I'll qualify that a little bit. So naive Bayes being, logistic regression being better, right? So naive Bayes posits a model for your x's and your y's, right? It's actually giving you a model over your x's. If that model is in fact true, if that model is true, it typically will learn faster than logistic regression because it has a better structured model that can model the data. On the other hand, if that is not true, if your variables are not independent, conditionally independent, given the output, then it will not do better. In fact, it will converge to a suboptimal point because it's trying to enforce a certain independence assumption that's actually not there in the data. So it can be better, naive Bayes, in that it will learn faster when the assumption is correct, but it also oftentimes will not perform as well in the limit of lots of data because your assumption could be wrong, and therefore you won't learn as well. Okay, so moving on. hypothesis testing. All right, so the majority of the lecture is going to be on hypothesis testing and experimental design. And this is going to be a very, very brief, like a lot of these things in this course, right? I'm used to sounding like a broken record, I'm sure. But it's going to be a very brief introduction here, and it's not going to get into a lot of the details. It's going to be kind of much more about illustrating a few examples of how you do hypothesis testing, or really sort of the math behind a few of the examples. And then giving some insight into why you might want to do this and what hypothesis testing really accomplishes from the standpoint of statistics. So let's start with a little bit of motivation. Well, here's the, so I don't know where this cartoon is from. It's hard to read on the thing. It's somewhere on the internet. I saw it on some professor's door once when I was back in grad school. So the thing I'll say to begin with here is that for a data science course, we have not done a whole lot of science yet. In fact, very little science have we done, right? We've been doing, data storage and processing, which is kind of engineering and software engineering. We've been talking about machine learning, which people think might be science, but really isn't science. And I say that as someone that does machine learning. Machine learning typically is not science, and I'll take that actually. I feel that very strongly. Science, by what I mean by that in this course, is trying to assess some actual truth in the world. So trying to determine if some effect or some relationship actually exists, not just in our model, not just to make things work better in our model, but it actually exists in the real world out there, which is actually much more rare than you might think in machine learning, right? Oftentimes we devise very complex algorithms whose ultimate goal is just to get good performance on some task. It does not mean we're necessarily actually trying to posit any true structure or true relationship in the world. We're just saying this algorithm performs well on this loss function, right? I got into a little bit about this, maybe kind of hinting at it when I talked about evaluating your algorithms, right? On training sets and testing sets and cross-validation sets, but it's still not really there. So this, you can't really read it, but this cartoon is about a mad scientist, and he says, why did you build a death ray to take over the world? And what hypothesis are you testing? Are you making mad observations? Look, I'm just trying to take over the world, that's all. And you at least have some kind of control group, right? And the point being that most mad scientists are really just mad engineers, because they're not actually trying to prove anything about the world. They're just trying to build something that takes over the world. And this is actually, I mean, this is a joke, but this is actually true of, I would say, most machine learning and most data science. Well, it depends on what kind of data science you're doing, but a lot of data science that's actually done in practice is not real science. And I say that with no sort of not disparaging at all. I think it's fine to not be scientists, but be aware that you're not really, for the most part, trying to prove anything about the real world. But sometimes you do, right? Sometimes you actually want to ask scientific questions about what is genuinely better. So one of the most common tasks that some data scientists do at some companies, this is actually a small subset of all data science jobs, but some subset of them essentially trying to show that certain designs of websites, for example, work better than others, right? So a big company wants to redesign their web page. Maybe they want people to spend more time on their web page. So they do a big redesign, or they have many possible redesigns, say. And they want to know which redesign should they do to make sure people spend the most time on their site. Now, I would say that is actually a scientific question, right? You are trying to answer the question, which version can I give to you? Which version should I give my users such that they are more likely, in the real world, that they are more likely to spend more time on my website? Alternatively, maybe I want to talk about linear regression, right? I want to talk about, and I talked a little bit about these models beforehand, but if I build a model of power consumption as a function of temperature, and as well as other features, I could ask the question, does power consumption vary based upon whether or not it's a weekday or a weekend, right? So that question is actually a scientific question. It's saying, is there an actual relationship in the world between being a weekday or not and energy consumption? And I think always falling back just to sort of good prediction in these cases. So maybe you would say, well, I don't really care about the real world. I just care about predicting well, like I do in machine learning anyway. And that way I'm going to, put up a prediction that I think is good. But especially when you start talking about things like, OK, I've run my website now, 50 users and they spend X amount of time on the first design and Y amount of time on the second design, does that mean that there's actually more, that there is actually value to this redesign? With 50 users, what about 1,000 users? What if I have this much margin difference between these two and this one versus this one? And so it really is important sometimes to think about these sort of scientific questions. All the election websites are another good example, right? They're not just trying to predict things. They're trying to actually say, right now, what is the true state of support for the different presidential candidates, right? So these are very valuable to think about. And the reality is we're not going to spend that much time on this. This is the domain of statistics in general, I would say. It's, how do you make inferences about reality from data? But I'm going to spend a little time in the class today talking about this and thinking about how we might approach these problems. All right, any questions so far? It might also sound like kind of a minor difference, but I think it's actually a very important difference because most people in machine learning, like I say, don't really care about uncovering a valid truth out there. They want to build a good performing system, which is a very different. I mean, they're related, of course, but they often can be very different goals than sort of finding truth in the world. The level, the bar is also much higher when trying to prove, or at least trying to confidently show that you can't disprove that there's some effect in the world. Okay, so let's talk a little bit about now some background, and this is, I'm sure, going to be familiar to anyone that's taken the statistics course before. Probably most people here, I would imagine, but I want to sort of set some notation because I use a little different notation than traditionally used in statistics. So let me just sort of mention a few terms that are hopefully common to people. So fundamental in statistics is this notion of a population and a sample. So the population, which I'm drawing as the big blob here, is the set of all the things you want to know about, right? The set of all people in the world, the set of all all days that are ever going to happen for power consumption, et cetera. It's the set of everything. Whereas the sample is a small subset of that we actually get to look at, right? When we're making our statistical inference. And in fact, almost all of what I talked about thus far in terms of estimation and estimating parameters of distributions, that actually was referring much more to the population statistics. So we're actually referring to how can we estimate certain properties of the entire population. And for example, we would do things like say, suppose the population is a Gaussian distribution. What's our best estimate of the mean and the variance of that distribution? But that is not the same, and we do it from a sample, but that is not the same as the actual statistics on that sample. So I want to be very, very precise here. And I'm also going to use here the terminology or the notation that statistics typically uses for these things. So the mean of the population is denoted mu. We've seen this before, right? This is just the expectation of a random variable. And the variance is denoted, oops, there's a sigma squared there. Sorry, put a little square here. Sigma squared is the expectation of the random variable minus its mean squared. Those are the things that hold true for the population. So they are saying, of my entirety of all the data that I could ever have, what is the expected value of that, and what is the variance of that population? On the other hand, I also have what's called a sample, which is a finite subset of, in our case, we'll be using M. Statisticians use N always. I'll keep using M because I used it for my other machine learning stuff as well. So be aware that I'm using a different letter there. But I have some sample of M elements drawn from that distribution. How do I go about estimating what those things are, what the mean is and what the variance is? So I already sometimes talked about this a little bit, right? When we talked about maximum likelihood estimation, I gave one formula for how you might come up with estimates for the true mean and the true variance here, right? And those would always typically posit some model. So we say, suppose that the data is Gaussian, or suppose it's from the Laplace distribution. Given that, here is the most likely setting of the parameters to maximize the probability of the data under that model. But you can also take a little different approach and just set, kind of, again, this is kind of the thing you would sort of obviously do, is you set the population mean to just be the mean of your samples. which is, by the way, the same as it was for Gaussian. It's almost always what you use as the estimate of the mean for any distribution. But this is a little different. There's no distribution we're sort of talking about here. We're just describing our sample. Similarly, we can also form an estimate of the variance of our sample. Sorry, an estimate of the variance of the population based upon the sample, which is called the sample variance. And here again, like in maximum likelihood estimation, we take our variables, we subtract them from the sample mean, we square that. Then we do something a little strange here, which we divide by m minus 1 instead of m. So if you remember, for a Gaussian distribution, the way we would estimate the variance in the maximum likelihood case was that we would just take this thing minus I called x bar the mean because it was our estimate of the mean, and we would divide by m. And here we're dividing by m minus 1. And I actually have the proof for why we do this written down later. But the intuition here is that these are actually a slightly different kind of estimator than the ones we saw in maximum likelihood estimation. These are what are called unbiased estimates of the population parameters. So we're again trying to estimate the population parameters. But here, unlike maximum likelihood estimation, we're not assuming any distribution over the hidden variable. So I'm not assuming any sorry, not the hidden variable, the random variable. I'm not assuming a Gaussian distribution, say, over x. I'm just assuming that x is just some variable, and I want to estimate its mean and its variance somehow. And I do that by forming x bar, which is just 1 over m, sum over I, xi, and then sigma squared, or sorry, not sigma, s squared, equals 1 over m minus 1 of xi minus x bar squared. The reason we do this is we do this such that the expectation of this thing, this is sort of a preview to the next few slides, which I'm not actually going to go through there. It's the math's there if you want to know it. But the reason why I do this is I do this in a way so that this is what's called an unbiased estimator of the population variance. So if you actually draw many different random samples, a lot of different possible random samples, compute the variance this way, and take the average, the mean value of those variances, what you actually find is this equals the population variance. Whereas you don't get that if you have m there. Of course, for a big enough sample, these are almost the same. But you'll always see this in every stats textbook, because this, when you're estimating both the mean and the variance simultaneously, this is the formula that you use. Yeah.
Intuitive insight as to why this happens?
Sure. I don't know if I want to get into that too much because it's. I have the actual formal proof of this very fact later. The idea is kind of that the mean that you estimate from the samples will always lie within your samples, right? Whereas in theory, when you actually have, if I have all my population take on values in this whole line, say the mean is here, I could get these samples here, their means between the two, and so this number here is less than this and this. And so you tend to underestimate. When you're using your own mean estimate, you tend to underestimate what the variance is, and so you need to inflate it a little bit. Now, why m minus 1 is the right term there, that just falls out of the proof. And in fact, maybe getting to that, but maybe I should have had this slide first. The point I kind of want to actually dwell on a little bit here is that we think of our x bar, our estimate of the mean. We want to think of that also as a random variable. So I'm going to, because x bar here is just equal to a sum of random variables, and then divided by the mean there. So it itself is also a random variable, right? So I can draw multiple samples, multiple different samples from a population, compute the mean of each of them, and that therefore the mean of the distribution of the sample itself is acting like a random variable itself. In fact, it's just equal to, well, I have it right up there. It's just equal to that, where each of them are random variables, and so the sum of random variables is also a random variable. And there are some very nice properties here. What's nice about this is that this random variable can be much better behaved than the random variable x itself, right? So first of all, two quick facts here. The first is that, not surprisingly, the expected value of the mean of the samples is just equal to the population mean. Hopefully that, it couldn't be anything else possibly, right? That just follows from linearity of expectation. And the second thing is that the variance of this thing, the variance of x bar, is actually equal to the population variance divided by the number of samples that we have. And this is very nice. What this is saying is that if I'm taking 100 samples and I'm estimating the mean of those samples, that mean, thinking of that mean itself as a random variable, that has much less variance than our original variable x, right? Because we're dividing our variance by m. And this follows from actually linearity of variance for independent, sorry, not linearity actually, but it follows from the fact that the variance of things, of two random variables is the sum of their variances when those variables are independent. It's not wholly not independent, but we're assuming these things are all independent. The x's are all independently drawn, and so you can actually add their variances like that. If you're curious about where the 1 over m squared comes out, actually, if you multiply a variance by a constant, that number squared times the variance is equal to that. But hopefully, don't worry too much. Just know that this is the formula that comes out for what the variance does. We also will typically estimate this, though, not with sigma squared, because we don't know the variance of the population. So we'll actually estimate this with our sample variance squared. So this is approximately equal to s squared over m. And so when we need an estimate of the variance of the sample mean, we will use this quantity in our estimate. And the square root of this quantity is called the standard error. So the square root of this is the standard error. Okay, and finally, I'll have questions after this, I think, because I think there should be some questions. But finally, the last point I'll make is that not only is this variable nice because it has smaller variance than our original population, right? So the mean, it's the random variable that is the mean has smaller variance than the original random variable. It's even nicer than that, it turns out. Not only is it smaller variance, it's also actually typically, in most cases, for large enough sample sizes, this variable here, x bar, will actually have a normal distribution with the mean equal to the mean of the population and the variance equal to sigma squared over m. And this is something called the central limit theorem. This is just a statement of what's called the central limit theorem. So big picture here. We have some population. We take a sample, and we compute the mean of that sample. That mean is itself, you can think of as a random variable, right? Because it will depend on our sample. And we can sample multiple different times. We can grab multiple different samples and have different estimates for the mean. But this mean, unlike our original variable, can be very nicely behaved. In other words, it approaches a Gaussian. I should probably put it more like this. It approaches a Gaussian distribution. And it has this mean and this variance. It's also sometimes written that if I scale my variable, so written like this sometimes, but you can also equivalently write this, that x bar minus the true mean over sigma over root m. When I scale a random variable, I divide by the square root of its variance, which is the standard deviation, not its variance. This variable here has mean 0 and covariance 1. Now in practice, this is actually not quite right, because you actually want to, when you have a sample estimate of your variance that you're using instead of your actual variance, you need to use a different distribution called a t-distribution, or a student's t-distribution, rather than normal. But this is getting into details I don't really want to spend too much time on. Just know that you have to use a student's t-distribution here, not a normal, for the central limit theorem. Or at least in practice, it typically holds better. It's a little bit wider-tailed distribution that accounts for the fact that you actually don't really know this term here, and so it can have a little bit wider spread in your estimate of the mean. Okay, so I realized that was all a little bit high level here. Hopefully, actually, have people seen some of this before, at least, in a stats course you've taken? Who's seen this before in a stats course? Okay, most people. Okay, good. So if you haven't, come chat with me. This is meant to be kind of a review, but hopefully it's refreshing some things in your mind. Any questions? Yeah.
So you're saying that it approaches a normal distribution?
Yes.
Like, so in cases, things like really heavy tails would affect it?
Right. So what's actually interesting is that this is a fact that is true regardless of the distribution of the original variable x. So the fact that the mean approaches normal is true almost. I mean, there are some conditions on it you need to have. It has to be bounded and things like this. But it's almost true regardless of that. Now, I'm not saying anything here about the rate of convergence. So it is true that the nastier your original distribution is, the longer it will take to converge to a normal distribution, the more samples you need before your sample mean starts becoming normal. But in practice, it isn't that many. Certainly for any bounded random variable, it approaches very quickly. So if your variable is ever bounded, it approaches very, very quickly. So then you can't have a heavy tail in some sense, but it approaches very quickly. If it's not bounded, yes, you can have some pathological cases where it takes a long time. But this is one of those things where it's sort of the practical statisticians always say that they use central limit theorem because this has this beautiful theory behind it. That's why they use the Gaussian. Whereas the theoreticians say we use the Gaussian because all data actually looks like it. So each side kind of pawns it off to the other side about why they use this. The reality is that yes, you can definitely come with situations where this will not happen. Of course you can. But for a huge number of variables, this will happen. And certainly for any bounded variable, it will happen. Again, regardless of the distribution of the underlying variable, if it's bounded, it will converge to a normal distribution. All right, so I have one slide here showing you the proof behind the m-1 scaling, if that was always a mystery to you. Essentially, what you can show is if I take the expectation of this thing, which is the undivided, this thing that's not divided by 1 minus m, it's equal to m minus 1 times the variance. So in order to get it to be the variance, I have to divide by m minus 1, of course. And the reason this works, well, these are the 3 lines of why it works. You basically distributed out this thing. You notice that some terms can be combined here, and you get actually a term that looks like m times the variance, and then m times the variance over m for this term here, which then equals m minus 1 times the variance. And so hopefully between going through this, if you really care about it, and the intuition I mentioned a little bit before, you start to see why that might be the case. The fundamental principle here is that if you just like the sample mean is a random variable, so is the sample standard deviation. And the expectation of that random variable, when you have this scaling term right, is equal to the actual population standard deviation. Again, when you have enough data, it doesn't really matter what you're doing because they're about the same. M and m minus 1 are very, very similar. But when you have a small amount of data, it actually can matter. So you should use the right one. All right. So let's then get started with basic hypothesis testing. So using these sort of basic principles, and they are very basic right now. And I should emphasize also that what we're about to do right now is incredibly sort of simple when it comes to hypothesis testing, maybe overly simplistic actually. But the basic thing I'll say is that using these simple principles of the fact that the population mean has a certain variance and becomes normal or becomes like a t-distribution after a certain number of samples, these basic facts can actually be used to actually make some statements that, if not proving things about the real world, because you actually can never prove anything, right? You could always just be unlucky and get a really good sample or a really bad sample. But these basic techniques can be used to sort of at least give us good confidence that some property actually holds in the real world. And the typical way to do this is through what I've talked about here called hypothesis testing. And the thing I'll say, and I'll preface all this by saying, is that there are a lot of caveats about hypothesis testing. To the point, in fact, where some statisticians would claim that we should never be doing this because it's just creating mistaken impressions of people about what statistics is actually saying about the world. I'll highlight a few of these at the very, very end of the talk. But for now, just know that there's lots of issues with things like interpreting p-values and stuff like this. But it's still incredibly common in practice. And in some sense, it may be the best thing you can do still. So there are alternative methods there are many alternative methods. Bayesian hypothesis testing is a common one that doesn't have quite some of the same pitfalls of these things. But the reality is that these techniques here are by far the most common ways to assess confidence in sort of real world situations. And so as data scientists, you should probably know how to run a simple test to know whether website A or website B is actually giving you more better traffic with some confidence. All right. Who actually, by the way, has also seen hypothesis testing before or has covered it in a basic stats course? Okay. So again, actually maybe not quite as many, but still most people. Or you're just getting tired of raising your hand. All right, so I'm going to stick most of the high level here with a few specifics of how we actually do this. I'm not going to go through examples. We'll go through some examples in the homework of these things you can actually work through. Oftentimes examples involve a lot of like looking up tables. And you don't have to do that anymore. You can just compute these things manually now. So we'll do some of that in the homework, but this will be more sort of the actual formula behind it. All right, so the basic idea about hypothesis testing is that we are going to posit what's called a null hypothesis. And this is sort of very, very crucial to the whole endeavor here. I'm going to state something which I'll call H0, which is the null hypothesis. I'll talk about what this can mean in a second, but basically it's something like if you're testing whether a website redesign has an effect, maybe the null hypothesis is that the two sites are the same. There's no difference between these two sites. And I'll cover some of these actually in a second. Oftentimes, a null hypothesis will be something like a certain variable has mean 0, so that there's no effect of some treatment you're applying. The difference between the control group and the actual treatment group is 0. So this is called the null hypothesis. This is the thing that we are supposing to start out with. And then there's the alternative hypothesis, which we'll call H1. And this, for the most part, I think for what we're talking about here, basically is just going to be just not H0. For the most part. It doesn't have to be that. It can be actually just something else besides that. But for our case, we'll basically think about the alternative being the null is not true. And then given some data X, and we can think of this sort of refer to it generally, but it's going to be usually a set of samples from some distribution or from some process that we're trying to make a statement about. We either want to reject or accept the null hypothesis. And the basic premise of hypothesis testing is that this is not a symmetric relationship here. So if H0 is true, in other words, the null hypothesis is true, and we accept it, that's correct. If it's not true and we don't accept it, that's actually not the case. But there are these two other possibilities, right? And the idea here is these are not equivalent. You have a type 2 error, which occurs when the null hypothesis is not true, the alternative is true, but you still don't reject the null hypothesis. And that, at least in most cases, is typically thought to have fewer consequences than the other type error, which is when you reject the null hypothesis despite it being true, which is called type 1 error. Now, I think the intuition there is something like, these are often formulated in the context of like drug studies, right? Where if you're going to propose a new drug to treat people, right, you better be very sure that it actually has an effect. All right, so if you take a drug that works and says that it doesn't work, I mean, maybe that's bad for the company. They spend a lot of money investing in it. They have to go back to the drawing board to do some more development. But if you take a drug that doesn't work and you put it on the market, telling people it will work, right? That seems to be a much sort of worse scenario. And so typically people think about the thing you want to control, the thing you want to get under control. I shouldn't use the word control, but the thing you want to reduce is the probability that you actually reject the null hypothesis, given that it's true. And this level, or rather, the lowest possible level at which you can reject it, even though it's true, is what's called the significance of the test. So a test with 0.01 significance means that the probability of the results you saw, given that this thing is true, is going to be less than 0.01. And similarly, the power of a test, which is different from this, the power of a test is the probability that you actually do reject the null hypothesis if in fact H1 is true. So this probability here is called the power, and this probability here is called the significance. All right, so here now is the basic approach to hypothesis testing. What we're going to do is we're going to compute the probability. So in some sense, we want to be conservative and only reject a null hypothesis if we're very certain that the data could not have been generated, or is very unlikely to be generated under this null hypothesis. And so what we're going to do is we're going to compute the probability of our data X given the null hypothesis. So what we're going to do is we're going to compute the entire distribution of what we would expect from our data, given the null hypothesis being true. And we're going to use that to determine, is our observed quantity just so far outside the bounds of normal that we feel confident saying that we're going to reject this. That's the methodology here. We're actually not really evaluating, you'll notice, H1 there. We're just saying, we'll get to the H1 in a little bit, but actually I think oftentimes as long as H1 is just not H0, you can think of it just in terms of H0. What we're saying is, let's suppose that H0 is true. What do we expect to see? And only if we're, again, really outside those bounds do we actually go ahead and say, OK, I'm going to not accept this null hypothesis now. And in fact, this quantity here is something called a p-value of the test. So this, because we reject if this probability is less than some significance level, the p-value would be actually the lowest significance level that we could have at which we would still reject the null hypothesis. Now, what's really important here, and this is, I mean, despite the fact that we all say this, and it's really easy to write in terms of conditional probabilities, this is an incredibly common mistake when people talk about these things, like in newspaper articles, right? So people often say things like, this test is significant at 0.000 or 0.001, meaning that, actually, how is it usually phrased? Meaning that the chance of this being generated by, the probability this is generated just by chance is 0.0001, which is not the case. This is not equal to the probability of H0 is true given the data, right? And this is oftentimes what people actually think that they're talking about. I mean, not statisticians, because we would never make this mistake, of course, because we're data scientists. But it's very common to see this sort of in print, sort of casually mentioned as the probability that the probability that this is due to chance is 0.0001, which is not the same thing, right? That is the probability of H being true given X. We're talking about the probability of X under the assumption that H is true. So you cannot equate those two things. Yeah. Where did I say that? Oh, yes. It's also not equal to this one either, but that's a little less interesting maybe. Yeah, let me fix that right now. Should have fixed the squared too in the previous slide, but come on, there we go. Okay, so just keep that in mind whenever you read about hypothesis tests, that what they are saying is, what the p-values say is the probability of your data given that the null hypothesis is true. And this, by the way, actually raises a lot of questions about whether this is even a good thing to measure. I mean, do we really care about this? I don't know. I think we care more about this in some sense, right? We kind of care more about what's the probability of these hypotheses given the data. And this is not what we're measuring here, right? So there's some argument about whether this is even a good thing to measure. And I think this is actually one of the statements that people advocating for Bayesian confidence intervals would really, or Bayesian statistics would really emphasize, is that this is meaningless to people, whereas this one is actually quite meaningful to people. And you can get them with the right, you can move between them with the right priors and these kind of things using Bayes' rule, right? But that's what we should be doing. We shouldn't be using p-values for hypothesis tests. Yeah?
The second one creates some bias when choosing for the hypothesis.
The question was, wouldn't the second one create some bias in choosing for the hypothesis? I'm not sure how to parse.
So to get the probability up, like wouldn't it create a bias for modifying your hypothesis in ways that fit the data better?
So I'm not actually talking at all about this one. I don't want to make any claims about this because I'm not going to be Bayesian here. I'm going to just be talking about normal hypothesis testing, which is just saying this. So there's no notion of the probability of a hypothesis being a prior to the hypotheses. There's no notion of any of that because it's tricky also. But some would claim better. So just know that there are other ways of doing it, but I'm not going to talk about them. Okay, so let's talk about now the canonical example, which is a t-test. So probably everyone, if you've taken this before, you've seen a t-test before. The idea is we have some sample, and we want to know, is the sample from a population with mean 0 or not, for instance. And the way we can do that is we can compute a test statistic, which is, in this case, what I should say is, if the mean is 0, then this quantity, x bar, divided by the sample standard deviation, or the sample deviation divided by the square root of m, that will be distributed according to a t-distribution with m minus 1 degrees of freedom. That's our kind of modified central limit theorem that actually takes into account the sample size and all these kind of things. Degrees of freedom is just a parameter, a free parameter in the student's t-distribution. I wrote it there before, but it isn't really that relevant. Just know that the fewer degrees of freedom you have, the wider tails that this distribution has. this thing would be equal to a t-distribution with m-1 degrees of freedom. So in order to compute our p-value would just be equal to the probability that, so I'll call t, well, actually what I should really say is that I define my statistic t equal to this thing. And the probability of my p-value, just the probability that x will be either less than t, I guess less than the negative absolute value of t, right? Can be less than, it could be, the mean could be either much more negative than 0, or the mean could be much more positive than 0. And this becomes my p-value here. I can compute this just by plugging actually these things in to the cumulative distribution of the student's t-distribution. But let me just show that visually, because it's kind of confusing to actually see that here. What I'm really saying, and this is actually the picture you should have in mind for every hypothesis test, is what I am actually drawing here is I am drawing the probability. So if this is the mean, what I'm drawing here is I'm drawing the probability of the sample mean given my null hypothesis. And all I want to do is say, I then actually have, this is the distribution I would expect to see given the null hypothesis. Then I have some actual example here. This is my actual sample mean that I get. And the question is, what's the probability that I get that extreme of value? Right? And that would just be the area, that extreme value or more extreme. And that would just be the area here plus the area here, right? Because you could talk about more extreme also being on the other side as well. So the area under this curve here, let's draw a little bit. Maybe I'll draw it like there. The area of these two parts there, that's the p-value. So that's the picture to have in mind for every hypothesis test, actually. What we're doing is we're coming up with a distribution of our desired. It doesn't have to be the mean. It could be any random variable. It's a function of our distribution. We have some distribution we expect to see given the null hypothesis. Then we plot where we actually see that statistic, from the data, and say, is that weird or not? That's the basic idea. That's all we're doing. So this could be some other distribution. If you have, other functions, then these are other distributions. And you plot where your statistic lies. The only question is that strange or not? Right? So this one, I would say, maybe looks strange. Maybe. You really like something like way over here, right? So like this point, that would be really strange, right? So I'd be very confident in saying that's strange. All I can do without sort of having a set threshold for strangeness or not, and people do have set thresholds for strangeness, sadly, is that I can just say, well, I'm going to compute the area, something like that, or weirder happening. And that's my p-value. This is all very, very easy, I should say, to code in Python. So I have some set of random variables x. In this case, they actually are random normal. So this hypothesis test should not reject the null hypothesis, ideally. But I compute my mean of the samples. I compute my sample standard deviation, which is the sum of the things minus the sample mean squared divided by m-1. I compute my standard error term, which is the square root of this, the variance of the mean, x bar. And then I compute t, which is just x bar over my standard error term. So this term is the standard error. This is my mean. This is my test statistic t. Then now the sort of the part where people used to say, okay, and now you have your test statistic, look up in this big back of your book, look up a table, see where it falls in the table. We don't have to do any of that anymore because now we have functions in Python that will just calculate the CDF for you. So you can just take basically your t statistic, create a t distribution with that many degrees of freedom, and plug it in, and you get something very nice that sort of is exactly what you want. You can also, by the way, for this one, just also run stats.ttest_1sample, where this thing here is the mean you're comparing to. That'll also work. But it's really easy to do. It really is just those 5 lines of code or so. No more looking up tables, which is really nice. We don't have to do that for anything anymore, thankfully. A few quick comments here. There's also this notion of one-sided versus two-sided tests. So what I've described so far is a two-sided test, in that we're actually testing that something is, at this level or more extreme, but on either side, right? Where it can either be, the mean can either be well above what we'd expect, or well below what we expect. And there's also the alternative, which is a one-sided hypothesis test, which says rather than this being 0, which is greater than or equal to 0, and I will actually, my alternative is just that it's less than 0, my mean. And that actually corresponds to just taking this side of the distribution when computing my area. Right? And by the way, I can have a bigger portion of area here, right? If I want to have, 0.05 or less underneath in the shaded area there, I can actually take a bigger, have a larger observed mean and reject my hypothesis if I use a one-sided test. So it actually has more power. But there are bad effects too. So what people will often do, well, not often, these are the stories that people tell about statisticians, but no one, of course, actually does, is that you'll run your one-sided test and it isn't quite significant enough. So you run a two-sided test, you run a two-sided test, it isn't quite significant enough. You get like a p-value of like 0.06, and so then you run a one-sided test to make up for that, and now all of a sudden it's significant. Don't do that. You can't do things like that for the same reason you can't use your cross-validation set or testing set to pick your best number or best error to report for machine learning. But all sorts of things happen. And in fact, I'll show a slide at the very end that has an interesting effect you see about p-values in papers. The last thing I'll say too, before I get into a couple more advanced examples, is mention that also very closely related to hypothesis testing is something called confidence intervals. And the idea here is that instead of saying that instead of just trying to say we reject or accept the null hypothesis at some level, we actually here try to give some range in which we expect the true mean to lie. So if I estimate my parameter, x bar, then I know that x bar, and this is actually forgetting about null hypotheses at all here. I'm just talking about x bar. I know that x bar has mean mu. Well, actually, I know more than that. I know it is actually this same thing happens before, right? Here, but here we have this minus mu equals this thing. And so what I can do is I can actually now compute. Right, before I was talking about just the null hypothesis which had mean 0. Here I'm saying that for any mean this will actually be true of the sample mean. So what I can actually do is get a range in which we expect this to occur. And so if I want to say I would expect that 95% of the time my true mean should lie in this range, what I actually do is I just manipulate this expression here, and I say that x bar minus mu is distributed like S over m, the standard error times our t-distribution with m minus 1 degrees of freedom. And then what I can do is now find the levels of this distribution that correspond to a certain portion of the area being under the curve. So that's sort of a little bit complex to say, but all I'm really doing here is I'm looking, I'm saying, I'm kind of flipping this picture around now, and saying that, if this is my mean, my sample mean, then I would expect, because, well, actually, no, I'll leave it this way. I'll erase the null hypothesis, though. This is my mean. Then I would expect the sample mean, x bar, to lie within some shaded area here, where this is, say, now I'm shading the other area, but this is, say, 95% of the total area under the curve. If I evaluate, how big of a spread this is until I get 95%, then I can say two things. I can say that, that x bar equals the mean plus or minus that, but because they're equivalent, I can also say that the true mean now lies within x bar plus or minus some things. So basically what I do here, I'll comes down to it is I can say that the mean is equal to my sample plus or minus my standard error times, and I'm going to use the notation here, F inverse 1 minus alpha over 2, where alpha is my confidence is my significance level, so that's like the 5% before, and this just is the inverse of the cumulative density function. So I'm looking basically for what level, how far do I have to go over here until I get 95% within that region. And again, before this was a total pain because to find the 95% confidence interval for a student t-distribution with m degrees of freedom, you have to look up in a book and say, okay, here's my distribution, here's everything, and now you can just compute this using what's called the PPF function, which is just the inverse CDF in SciPy stats kits. Any questions? All right. So I realize we're going a little fast here, but I want to say a couple more things. And from now on, the actual math, the actual numbers I write here are no longer important. Just know that you can do these things and you can look them up. Again, the big picture for all these things is, the way these work is I come up with my null hypothesis, I come up with my distribution of what I expect my statistic to be given that hypothesis, and then I ask myself, is the thing that I'm actually observing strange or not? That's what all of them are doing, and that's just how these hypothesis tests are working. So all of these things are just an instantiation of that. All right, so up until now, we've assumed that the null hypothesis is something we know the mean of the null hypothesis, right? That we know that we're comparing to the mean being 0 or something, right? But typically, that's not the case. You don't know with certainty anything. Everything's estimated from samples. So if I have, say, some website, right, how do I know how much time you just spend on my website as it's currently designed? That's just a sample too, right? That I've estimated that from a bunch of data, maybe a lot of data, maybe not that much data. And so we actually, in most cases, need to form a hypothesis which is actually defined in terms of two groups. And these groups have the common names everyone knows about, but they're called control and treatment groups. So the typical way we define an experiment is that we separate our whole population. We actually draw two samples of our population. One sample from the control population, which is the people that haven't been messed with in any way, or the website as it was originally designed. And then one group of people from the treatment group, which is the people that have been given some extra effect, or the people that see a redesigned website, right? And the idea of hypothesis testing in this setting, sometimes called A/B testing. Actually, A/B testing has a sort of a very website feel to it. People have been doing this from in medicine for ages. They didn't really call it that much A/B testing. That name took off much more when we're talking about websites. But the idea is here the null hypothesis is not that something equals 0. It's just these two means are equal, right? So the null hypothesis is that there is no difference between the mean of the first group and the mean of the second group. And our alternative is they are not equal, or maybe one's less than the other, right? And the same, we can have a one-sided or a two-sided test. So again, the basic idea here is exactly the same as before. We're going to come up with some statistic that captures the likelihood of our sample means under the null hypothesis. And in this case, we actually need a distribution over the difference between the two sample means. So what I'm going to do is I'm going to form sample mean 1, subtract sample mean 2, and come up with a distribution of what I expect this thing to be given the fact that they're equal. Right? And I'm going to compute a statistic, which I sort of observe being here, and I'm going to say, is that strange or not? And the way you do that, for this case, this is called an independent t-test or a Welch's t-test, is you compute your statistic like this. This is essentially a the difference in terms here, but where the standard error of the distribution actually takes terms from both standard errors together. So you may have different sample sizes for the two different groups, and they may themselves each have different standard deviations. And so you have to account for that in computing your statistic. And additionally, there's some really weird and crazy, which I don't even know why this is the case. There's some really weird, crazy rule for approximating the degrees of freedom in this case. You don't take m-1 to be the degrees of freedom. You take this quantity here to be the degrees of freedom, and you plug it again into your t-test, and that's that. Now, if this is seeming a bit ad hoc to you, I don't really blame you. What all these things actually do is they are trying to quantify what the distribution of these statistics is if I assume the null hypothesis. And when you have two distributions with different variances and different numbers of samples, then the central limit theorem actually gets a little bit more complicated. So the distribution they approach can actually be a little bit more complicated, but that's all it is. They're with enough samples, you're going to approach some distribution for your whatever statistic you want. So your difference of means, whatever this is. And then I'm just going to then evaluate, given my actual observed statistic, how strange is it? So you don't need to know. I mean, you don't need to know that, right? This thing, the fact that a Welch's t-test is of this form is not something you need to know or remember. But you should know how to look up which test you want to use if I have two samples with different sample sizes and with different with different variances in my population. How do I compare if one mean is bigger or less than the other? Or how do I compare, against the null hypothesis that these two means are the same? And you Google it, and then Wikipedia shows you it's Welch's t-test that you want. And when you have other things, you want other tests. And so that's sort of the extent to which you'll actually need to know this stuff as in most of data science, and probably, frankly, even less, because as I said, oftentimes you don't do any science as a data scientist. The very last thing I'll mention is that you can do the same thing, and this is actually very useful, but not done that often. And so I just want to highlight that this is possible. You can also do the same thing for the coefficients of linear regression. So remember, we had some linear model. We said, we suppose that our output is approximately some linear model times some input features. You can actually do hypothesis testing on the coefficients themselves. So this will be something like if I'm going to build a linear model to predict consumption of electricity, right? This is our example we used, and I want to know, is there an effect from the day of the week on my output? One way I could write that is to suppose that in my null hypothesis that whatever coefficient corresponded to my my day of the week variable, suppose that's 0, and the alternative is that it's not 0. This would be a reasonable way to test whether or not this variable has an effect in linear regression. And in fact, this is actually a generalization of these other methods if you want to look at it in a little more detail. We've already seen some ways to do this, but it can be difficult to understand what this means. So suppose I do cross-validation, and I get the result that there's this much coefficient. There's a 0.001 coefficient on my weekday variable. Is that significant or not? Is there actually an effect there or not? It's not always easy to do, even with cross-validation. So I'm just going to show the formula here. The basic idea is that you're doing something very, very similar to what we did before with estimating sample mean. The only difference is now you're estimating a sample standard deviation. You're now estimating a sample standard deviation on the errors of your linear model. This is actually how these things work. So I'm going to form S squared here, which is actually a measure of the area, measure of the error of my linear model. In other words, y minus the prediction on y. And I'm going to normalize by a different quantity now, which is the number of samples minus the number of features that I have in my linear regression. And You'll have to trust me here that the covariance of this thing is equal to the sample covariance. The covariance of the coefficients actually is equal to the sample covariance times x transpose x inverse. And you can use this to compute a t-statistic as well for the hypothesis that's equal to 0. And you can use this to actually do hypothesis testing on your coefficients, which is very useful, for example, if I'm doing a website design, but instead of just being is this website 1 or 2 better? Maybe I have a bunch of features in my websites. I've generated a bunch of different samples from these things, and I want to know which features actually correspond to people spending more time on the website. Okay, so this is the last slide I have, and I'll just I already mentioned the first problem a lot, so I'll sort of stick with that. The other thing I want to sort of mention is that there are all sorts of weird effects that have happened from people overusing p-values and also overusing 5% as a level which we call something significant. So these people a couple of years ago, 2012, did a study about, I think for about 3,500 papers from journals. They looked at what the p-values that were reported in those journals were, and they found there's a huge spike of p-values right around 0.5, or sorry, 0.05, which has traditionally been the level which you say, oh, this is significant statistically, and everything above that is nothing. So we have this horrible bias where we're not actually being honest about these things. The things that have 0.44999 as their significance level, 0.0499 are considered significant, whereas other things that are just above are not, which leads to horrible science in a lot of ways too. So these things are useful, but they can easily be abused. So be wary about the difference between the p of h0 given the data and p of the data given h0, and be wary about treating any single threshold as overly important above and beyond just what your common sense tells you. All right, so that actually ends our unit on a lot of basic statistics and machine learning, and we're going to start delving into a lot more advanced algorithms and kind of fun methodologies next time in class.